Hi there. In this project, we'll introduce the oscilloscope instrument on the analog discovery. Oscilloscopes, generally called scopes for short, are the most valuable tool available for measurement of electrical signals. They measure voltages like voltmeters do, except that they display a plot showing the behavior of the voltage as a function of time. Voltages are a difference in energy levels between 2 points, so we need 2 terminals to measure a voltage. On the analog discovery, the oscilloscope terminals are the same as those used for the analog discovery voltmeter. For channel 1, they're 1 plus and 1 minus, and for channel 2, the terminals are 2 plus and 2 minus. The comments relative to the polarity of voltage measurements that we made in our voltmeter introductory project are also applicable to oscilloscope voltage measurements. The terminals denoted with a plus sign, 1 plus and 2 plus, are connected to the terminal with the assumed higher voltage, while the terminals with a minus sign, 1 minus and 2 minus, are connected to the circuit terminals with the assumed lower voltage. Negative signs on the voltage measurement simply mean that the polarity is opposite to that assumption. One general comment about oscilloscopes before we get into our project. The analog discovery oscilloscope has what are called differential measurements. They measure a voltage difference between any 2 points in a circuit exactly like a voltmeter does. Many scopes, however, have what are called single-ended measurements. They always measure a voltage relative to ground. So make sure what kind of measurement the scope you're using makes. Using a single-ended measurement to measure voltages between 2 arbitrary points can lead to errors. Luckily, we don't have to worry about that when we're using the analog discovery. Just connect the terminals however you want and you should be okay. Since our scope behaves so much like a voltmeter, we're going to use a similar circuit to the one we used in our voltmeter introductory project. It's simply a 5-volt source connected to an LED with a resistor to limit the current. To illustrate the scope's ability to display time-varying voltages, however, we'll add this switch. This allows us to turn our light on and off. When the switch is closed, we apply voltage to the circuit and light the LED, and when the switch is open, no voltage gets to the LED and our voltages are 0. I'll implement my switch by simply plugging or unplugging the voltage supply terminal into my breadboard. We'll measure the voltages across the diode and the resistor with these polarities. I'll use channel 1, which is designated as C1 on the oscilloscope, to measure the diode voltage, and channel 2, C2 on the scope, to measure the resistance voltages. We switched the polarities of channel 1 measurement from our voltmeter introductory tutorial, so we should get positive values on both channels when we apply power to the circuit. Here's our circuit. We apply V+, the red wire on the analog discovery flywire, to the resistor. The resistor and the diode are connected here, and ground is connected to the diode's cathode. Channel 1, the orange wires, measure the voltage across the diode. Channel 2, the blue wires, measure the voltage across the resistor. To open the oscilloscope instrument, click on the scope icon in the Waveforms main window. We get this rather intimidating window with lots of buttons on it. Later projects will show how to use many of these features, but for the moment I'm just going to stick to the basics. The most important thing about the oscilloscope window is this main waveform window. It's in this window that the voltage as a function of time is displayed. The horizontal axis on this window is time, and the vertical axis is voltage. We can set the parameters of the waveform window axes by using these panels on the right of the oscilloscope window. The horizontal axis properties are set with the time controls here at the top. The base option sets what's called the time base. That's just the scale on the horizontal axis. Its units are seconds per division. The number you select here sets the amount of time between vertical divisions on the window. For example, if I change this to 200 milliseconds per division, the time between the vertical lines is now 0.2 seconds. The POS option stands for position. It essentially adjusts where 0 time shows up on the window. If I change POS to 500 milliseconds, 0 time shifts left on the main axis by 0.5 seconds. 0 time is also indicated by this inverted black triangle at the top of the window. You can also shift 0 time by clicking and dragging on this triangle. The vertical axis properties are set by the channel 1 and channel 2 control boxes. The vertical axes for each channel are set separately, so they may not share the same vertical scale. The vertical scale for the window is indicated in a color that's appropriate for the channel scale that's being displayed. I can click on the little tabs at the top left of the window to change the channel that sets the vertical axis display. The scale on each vertical axis is set with the range option. You input a value corresponding to the number of volts per horizontal division. For example, let's set the range on channel 1 to 500 millivolts per division. Notice that the vertical scale on the waveform window changes accordingly. The offset option sets where on the waveform display 0 volts appears. For example, if I set the channel 1 offset to 0 volts appears in the center of the screen. 0 volts is also indicated on each channel by the rightward pointing triangles at the left of the screen. You can change the offset by clicking and dragging these to where you want them to be. The last thing I'll do before starting to acquire some data is to set the trigger mode to none. This set of buttons here sets up something called the trigger. That'll be the subject of a later project. For now, I'm just turning the trigger off. To start acquiring data, click on the Run button. The oscilloscope now starts reading data from the terminals and displaying it as a function of time. At the moment, the voltages are 0, but if we turn on the power, we see that the voltages on the scope screen respond. Disconnecting the voltage instrument wire from the breadboard turns the power off and causes the voltages to go back to 0. Plugging the wire back in returns the voltages to their non-zero values. I can also change my time scales to change the rate at which data is being displayed. Or I can adjust my voltage scales on either channel independently. By default, if the time base is high or if the window shows a long time frame, the data scrolls past the window. Once it gets to the right edge of the window, it starts over again at the left side of the window, erasing the previous frame of data as it goes. You can modify the way this data is displayed if you want. Select View on the menu bar and click on Advanced Trigger. This will cause some additional options to appear in the available tools. By default, in the Run options, Screen is displayed. Let's change this to Shift. The main window will now shift to follow the waveform. Once the waveform reaches the right side of the window, the waveform will slide to the left so that new data points always appear at the right-hand side of the screen. If we select Repeat in the Run options, the oscilloscope will display one window's worth of data at a time. The window of data is refreshed all at once when the entire data set is acquired. We're seeing snapshots of the data in the main window. Notice that the display doesn't update until the oscilloscope has had time to acquire a full screen's worth of data. Since we're displaying 2 seconds of data, the screen won't update more often than once every 2 seconds. That's really all there is to the basics of oscilloscope usage. I encourage you to play around with these controls and get a feeling for their effects. It's important to have a good handle on the basic controls before proceeding with the more advanced oscilloscope features. Most other features depend on understanding these basics.